Hello and welcome to another episode of Maths with Mrs. Banks, where we make maths fun and easy to learn. And in this video, we're going to focus on Mathematics Grade 11 Paper 2, and this is Euclidean Geometry, to be particular, circle geometry. And these questions, the set of questions, come from the November 2020 paper of the Rondebosch Boys High School in Cape Town. Without further ado, let's get right to it. Question number 6 goes, in the diagram, ABC is a tangent to circle O at B. Here is ABC, that is the tangent. It meets the circle at B to the circle O. Prove the theorem that states that angle DBC, which is this angle. Prove the theorem that states that angle DBC equals to angle DEB, which is this angle. So step number 1 of our three-step proof plan. Step number 1, know your theorem. Let's know this theorem. Now, looking at the way the question has been structured, this is simply the Tan-Chord theorem. This is the Tan-Chord theorem. There are no words to describe or explain in detail. So this will be the Tan-Chord theorem. Just keep that in mind. Now, what is the goal? The goal is to prove that angle DBC is equal to angle DEB. That is step number 2. The goal is to prove that, we're required to prove that angle DBC is equals to angle DEB. Angle DBC is equal to angle DEB. This one is very straightforward. No manga business over here. Now, what is the strategy? How are we going to go about it? Number 3 strategy. The strategy is to join the point at which the tangent touches the circle and join that with the center of the circle and extend that line all the way through to the circumference of the circle, so you form a diameter, and the diameter is going to help us prove this theorem. And then after forming that diameter, join the point F where the diameter ends at the circumference and join that with a point D. So you basically construct an angle in the same segment with angle E. And we know automatically that that is equal. These two are equal. But why? We want to prove, using the strategy I'm going to explain in detail, we want to prove that angle F is equal to angle E. But also we want to prove that angle F is equal to angle B. How we are going to do that? Wait, I'm going to show you now. So number 3, step 3, the strategy. I'm going to explain the strategy in detail, but right now let's look at the main point. The main point is to prove that angle F, the constructed angle, which is in the same segment with angle E, is equal to angle DBC or CBD, DBC. Let's go ahead and do that. So the strategy is to prove, number 1, show that angle F, for the constructed angle, equals to angle E. So let's recap. The goal is to show that angle F is equal to angle E. The F angle that we just constructed, and we constructed it strategically in that it is in the same segment with angle E. All right. This one is very easy. But what we want to do is to show that this newly constructed angle is also equal to the angle between the tangent and the chord. So let's name the angles for ease of reference. So there will be X, and let's name that Y, and this will be angle Z or Z, whichever you prefer to use as a pronunciation. So now what we want to do is to prove that angle X is equals to angle Z. How will we do that? So we take this center and where the tangent meets the circle B, making or forming a radius, and then we show that this is equals to 90 degrees. We want to show using this that angle Z is equal to angle X. How we go about it, let's start. Show that angle F is equals to angle E, which is in turn equal to angle. We want to show that angle X equals to angle Z. We want to show that angle Y equals to angle Z, which is in turn equal to angle X. We want to show that angle Y, we want to show that angle X equals to angle Z, which is in turn equal to angle Y. X equals to Z, which is also equal to Y automatically. All right. So how do we go about showing that angle X equals to angle Z? So we use the fact that the construction. Okay, let's note the construction. Proof. The first thing is you construct that line join BF through center such that BF is the diameter of the circle. BF is a diameter. Now that we have a diameter, therefore OB is perpendicular to BC, meaning that therefore angle OBC or angle FBC is equal to 90 degrees. Angle FBC is equal to 90 degrees. Angle FBC which is equals to, let's make it angle X plus angle A. Therefore, angle X plus angle A, which is FBC, A plus X, that will be equals to 90 degrees, and the reason is radius perpendicular to tangent. Radius perpendicular to tangent. How does that help us? But notice that this angle BDF is equal to 90 degrees. Angle BDF is equal to 90 degrees, and the reason is it's an angle in a semicircle. Angle in semicircle because we've got the diameter subtending that angle. Angle in semicircle. Why is that important? Note that this angle A also belongs to this triangle BFD or BDF. It's up to you how you wanna. So therefore, because this angle FDB is already 90 degrees, therefore angle X plus angle Z, A plus Z, therefore angle A plus angle Z will be equal to 90 degrees because these are the two remaining angles in that triangle BDF. And the reason will be sum of angles in a triangle. Sum of angles in triangle. Alright, so notice that now we've got x plus a equal to 90 degrees and also a plus z equal to 90 degrees. So now we've got a plus z equals to 90 degrees and a plus x equals to 90 degrees. Now both x and z, when added with a or added to a, they give us 90 degrees. So meaning that therefore the common one, x and z, therefore x is equal to z. Now we've proven that x equals to z. Alright, good. So we're done with the first part, but angle z equals to angle y, and the construction, it's because of the construction, angles in same segment. Now because z is equals to x and that also equals to y, therefore we can conclude that x equals to y because they are both equal to z. X equals to y, both equal z. Now what is x? X is angle DBC and y is angle DEB. Therefore angle DBC is equals to angle DE, angle DEB. We've proven that. Easy peasy. You can rewind to get the essence, but here is a summary. Basically what we do is we construct a diameter, and that diameter will give us a right angle triangle which and an angle that is perpendicular. OB is perpendicular to the tangent because it's the radius. So now what we do is we show that if this a plus x equals to 90 degrees now, and also because this is 90 degrees angle in a semicircle, and a plus z is also equal to 90 degrees, therefore z and x are equal. But since the construction already is such that these two angles F and E are angles in the same segment, therefore y, which is already equal to z, will be equal to x. And basically that's how we strategize proving that theorem. And now let's use that in practice. 6.2 goes, in the diagram KLM is a tangent to the circle at L. KLM is a tangent to the circle at L. Angle NLM there is equal to 75 degrees, and angle JLN, this one is equal to 80 degrees. Determine with reasons the size of J1. Okay, we need to find size J1. Notice that J1 is the angle subtended by this chord. We're going to draw it in red. It's subtended by this chord. That's what J1 is. But this chord has an angle between it and the tangent, which is 75 degrees. Therefore, J1 will be equal to 75 degrees, and the reason is J1 will be equals to 75 degrees, and the reason is Tan-Chord theorem. Let's fix that. You can write it as Tan-Chord theorem or just simply Tan-Chord. That is also not a problem. It's very allowed, especially if you're in a hurry. It's a nice shortcut to use. Angle GHN, this is the angle. Angle GHN is equal to, notice that it's an exterior angle of a cyclic quadrilateral. Here is the cyclic quadrilateral. 4 corners all inside, of the circle on the circumference of the circle, so that makes it a cyclic quadrilateral. Now this is an exterior angle of a cyclic quadrilateral. It's supposed to be equal to the interior opposite angle, which happens to be 80 degrees, and therefore angle GHN is equals to 80 degrees, and the reason is exterior angle cyclic quad. Next question, angle N2. Angle N2, notice that angle N2 is subtended by this chord GH, which happens to be equal to the chord LN, which we've already figured out it subtends an angle equal to 75 degrees. Therefore, this angle will also be 75 degrees, reason being that equal chords subtend equal angles. So therefore angle N2 will be equal to 75 degrees, and the reason is equal chords JH equals to LN, JH equals to LN, equal angles, and you can write it like that. Equal chords, equal angles. And this question is done. Next question, question number 7, still from the same paper. All of these questions will be coming from the same paper. In the diagram, O is the center of the circle ABCD. AOD is a diameter. Here is AOD. It's a diameter, and OC is a radius. AB, BC, CD, AC, and BD are straight lines. All of those are straight lines. Write down with a reason the equation that expresses the relationship between each of the given groups of angles. Let's underline relationships because that's important. The relationship between each of the given groups of angles. An example has been given to you. So let's look at the example. We're given O1 and O2, and they say O1 and O2, when you add them together, they give you 180 degrees, and the reason is angles on a straight line. When you sum angles on a straight line, they give you 180 degrees. So when you're given these two, you know what and how they are related. Number 1, 7.1.1 goes D1 and C1. Angle D1 and angle C1. Now notice that angle D1 and angle C1 are subtended by the same chord, and this is the same chord AB. So therefore it's subtending this angle C1 and subtending this angle D1. So therefore they are equal. Angle D1 is equal to angle C1, and the reason is angles in same segment. Angles in same segment. Angle in same segment are subtended by the same chord. Angle O2 and B2, they are angle O2 and angle B2. Now notice that they also are subtended by a common chord, the same chord, and this is the chord that subtends them. And the chord subtends O2 at the center of the circle. This is the center of the circle as we were told. Chord CD subtends angle O2 at the center of the circle and also subtends angle B2 but at the circumference, and therefore angle O2 will be equals to 2 times angle B2 because O2 equals to 2 times angle B2, and the reason is angle at center equals to 2 times angle at circumference. Angle at center equals to 2 times angle at circumference. And that's the reason there. Next, B1, B2, D1, and D2. B1, B2, D1, and D2. These are opposite angles of a cyclic quadrilateral, and we know that they are supplementary, so they will add up to 180 degrees. So B1 plus B2 plus D1, angle D1 plus angle D2, they will add up to 180 degrees because opposite sides of a not a parallelogram, sorry about that, of a cyclic quadrilateral are supplementary, meaning they add up to 180 degrees. Opposite angles, cyclic quad. So that's how we end up with that. Next, D1, C3, and D2. Angle D1, angle C3, and angle D2. Notice that these are angles that for some reason somehow form a triangle, and we're going to highlight that triangle so that there are angles in the triangle, including this one. Let's also highlight this one. Alright, so D1 then becomes the exterior angle of triangle, this triangle, meaning that it is equal to the sum of the two angles in the interior. C2 plus D2 will be equal to D1. D1, angle D1 equals to angle C3 and D2, angle D2, sorry. And the reason is exterior angle of a triangle. Exterior angle triangle. That's the reason. And we're done with this page. Next question, 7.2. In the diagram, SP and SR are tangents to a circle. SP and SR are tangents to the circle with center O. There is a circle. Angle PRS equals to 61,9275 degrees. There is the angle. All right. Now the question goes, 7.2.1. Give a reason why SP is equals to SR. These are tangents from the same point S, and that's the reason. So the reason they are equal is tangents from same point. Tangents from same point. Next question. Prove that ORSP is a cyclic quadrilateral. ORSP. So let's join this so you can see the quadrilateral we are working with. Let's join this. Show that this is a cyclic quadrilateral. Now there are three ways you can prove or show that a quadrilateral is cyclic. Okay, let's take a look at them all. Cyclic quad proof. Reasons. Proof reasons. Okay, the first one is that you must have opposite angles supplementary. Opposite angles supplementary, meaning that they add up to 180 degrees. And the second one is that the angles in the same segment are equal. Angles in same segment equal. Angles in same segment equal. That's number 2. Number 3 is when the exterior angle of the cyclic quadrilateral is equal to the interior opposite angle. Interior opposite angle. If they are equal, then if any of these are met, the conditions, then you have a cyclic quadrilateral. Next question. Prove that ORSP is a cyclic quadrilateral. That's still the same. Let's prove. Now, looking at the diagram, which angle of proof will be best? Opposite angle supplementary, let's keep them. Angles in same segment, that could be difficult. Proving that angle POS is equal to angle PSR. It can be done though. It can definitely be done. It can definitely be done. And then another one, exterior angle equals to interior opposite angle. We do not have an exterior angle given to us here, so that is going to be a problem. So this one we can immediately eliminate, because there is no way we can prove this for sure and know that we are on the right track for sure. So let's eliminate this one. Now let's look at opposite angles. Supplementary. Notice that angle ORS is equal to angle OPS, and they're both equal to 90 degrees, and I'm going to show you the reason why that is the case now. 7.2.2, angle ORS, angle OPS equals to angle ORS, both equal to 90 degrees. And the reason is tangent perpendicular to radius. Angle OPS equal to angle ORS, both equal to 90 degrees. And the reason is tangent perpendicular to radius. So now each of them are 90 degrees and they're opposite each other. So let's add them together and see if they give us 180 degrees. Therefore, angle OPS plus angle ORS, that will be equal to 90 degrees plus 90 degrees. That is equals to 180 degrees. Yay, we've reached our goal. Therefore, that quadrilateral is a cyclic quadrilateral, ORSP. Therefore, ORSP is a cyclic quad, and the reason is it's a cyclic quad, and the reason is opposite angles supplementary. That was easy. Looked difficult, but that was easy. Next question, 7.2.3. If PS equals to 15 units, this PS. If this PS equals to 15 units, if PS equals to 15 units, determine the length of the radius of the circle. The length of the radius of the circle. Okay, the circle is this. The radius is this. Okay, let's call it X. Notice that the radius of the circle forms a right angle triangle with the side PS, which is 15 units. So now we need to figure out a way to find the size of an angle. This angle, for example. How do we find the size of that angle? Okay, from this angle, angle QRS is equal to angle QPS, and the reason is that these two sides are equal. We've already proven that. Okay, angle QPS (7.2.3) angle QPS is equal to angle QRS to 61,9275. ORS, which is equals to 61,9275. so this is 62, or it's 6, is it 61? Yes, 61 comma 9725, or 9275, sorry, 9275. Let's fix that. And this is 90 degrees, so meaning that this angle over here will be 180 degrees minus 90 minus that. Therefore, that angle, and that's angle what? Angle S2. Therefore, angle S2 is equal to 180 minus 90, 180 degrees minus 90 degrees plus 61 comma 9725. Well, let's see, 61 comma 9275, 9275, sorry, 9275, 61,9275 degrees. Alright, and that gives us an answer of, let's take out a calculator. The calculator is 180 minus 90 plus 180 minus, in bracket, 90 plus 61 comma 9275. Let me just double check. 9275, correct, and that gives us an answer of 28,0725. 28 comma 0, let's say 725. Now that we've got that, and we have a right angled triangle, so that's 28,72, 28 comma, this angle is 28 comma, so that angle is 28,0725, 0725 degrees. Now this angle, let's use it to calculate x. It's a right angle triangle, so the tangent of 28,0725 will be equals to x over 15. Therefore the tan of 28,0725 will be equals to x over 15, meaning that therefore x equals to 15 times tan of 28,0725, which is equals to, take out a calculator, 15 times the tan of 28,02725. Let's just double check. Correct, and that gives us 8,000, 8,000, blah 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 blah. Therefore x is equal to 8 units. Therefore x equals to 8 units, and this is the correct answer. And that was the last question for this page. Now let's move on to the next page. question 8 goes, in the diagram A, B, C, and D are points on a circle with center O. OB, okay, A, B, C, and D with center O. OB intersects AC, there it cuts AC at M. The midpoint of a chord AC. What is the chord? The chord is AC. Okay, this is the midpoint of the chord. Okay, let's put it out there so we can remind ourselves this is the midpoint. And we are told the midpoint of AC, D1, angle D1 equals to X. There is angle D1 equals to X. And the question is, give a reason why angle M2 equals to 90 degrees. Give a reason why angle M2 equals to 90 degrees. Why is the 90 degrees? That's very easy. The line from the center that bisects the chord is perpendicular. Line from center to midpoint. Line from center. Line from circle center to midpoint is perpendicular. To midpoint perpendicular. Midpoint of chord perpendicular to the chord. Midpoint of chord is perpendicular to the chord. You don't have to write this whole theorem, this whole essay. You can shorten it. Write down with a reason the size of angle A1. What is the size of angle A1? The size of angle A1 is very self-explanatory. It's an angle in a semicircle, so that will be equals to 90 degrees. Okay, so that is 90 degrees. A1 equals to 90 degrees. Angle in semicircle is the reason. Next, determine with reasons in terms of x the size of angle O2. In terms of x, what will O2 be? O2 is the angle subtended by the chord, by the arc BC at the center, and the same arc subtends angle D1, and angle D1 is x. Therefore, angle O2 will be equals to 2x, because the reason is angle at center equals to twice angle at circumference. Angle at center equals to twice angle at circumference. That is the reason. Next, angle ABO. What is the size of angle ABO? The size of angle ABO. Alright, we've got this one is 90 degrees, so meaning that this will also be 90 degrees. So we've got this sorted. 90 degrees. Alright, but notice that angle A2 is subtended by the same chord BC that at the circumference that subtends D1, so it is equal to D1. Alright, angle A2 equals to angle A2 equals to angle D1. These are equals to x. Angles in same segment, subtended by the same arc. Angles in same segment. So now what do we have? So that is angles in the same segment. Right, so this is x, and this one is 90 degrees, so therefore angle ABO, Therefore, angle ABO, right, let's write this one, right, 8.3.2, angle A2 is equals to angle D1 equals to angle X, angles in same segment. Angles in same segment. Alright, so we know that therefore angle ABO equals to 180 minus 90 minus X. Therefore, angle ABO equals to 180 minus the sum of those two that we already, okay, plus X, which is equals to 180 minus 90, that is 90 degrees, minus X. That is the size of angle ABO, and that is sum of angles in a triangle. Sum of angles in triangle. Okay, so that is 90 minus X. Let's go write it down just in case. 90 degrees minus X. Next, prove that AB is a tangent to the circle that passes through points AD and R. Okay, let's just construct that AD and R. There is the points. Let's just construct the circle that goes through these 3 points. Alright, let's go. Okay, let's, okay. Okay, let's fix it. Angle 8 there, it is perfect. Perfect. There is the circle that goes through ADR. Alright, there we go. So corner D, corner A, corner R are all on the circumference of the circle. So now we want to prove that AB is a tangent to the circle that passes through AD and R. Alright, if it is a tangent to the circle, therefore it means that this angle that is subtended by the same angle, this chord, the angle subtended by the chord, which is D2, will be equal to X. So what we need to prove is that, okay, we need to figure out what the size of D2 is. If it is X, then it means that AB will be the tangent. So we need to prove that this angle is equal to this angle. Tan-Chord theorem. So let's use that. Well, we already have A1 equals to 90 degrees. And then we have, okay, let's figure out what the size of this will be. Alright, so this is 90 degrees. This is what? Okay, angle B2 is equals to angle D1 equal radii. Okay, angle B2 equals to angle D1. Angle B2, that's number 8.4. Angle B2 equals to angle D1 equals to X. Let's just double check the coding. Angle D2, B2, yes. This is equals to X. Okay, and the reason is OD and OB are equal radii. OB equals to OD equals to OD. Okay. OB equals to OD equal radii. Therefore, those angles will be equal. So this is angle X. And then we already have 90 degrees over here. So this is 180 minus. Okay, so angle R3, which is vertically opposite to angle R1. Therefore, angle R3 equals to 180 minus 90 degrees plus X, which is 90 degrees minus X. So that is equals to 90 degrees minus X. This one. Meaning that angle R1 also equals to 90 degrees minus X. And that is vertically opposite. Therefore, R1 equals to R3 equals to 90 degrees minus X. And the reason is vertically opposite angles. Vertically opposite angles. All right. Now in this triangle DAR, we have therefore D2 equals to 180 minus that. Therefore D2 equals to 180 degrees minus all of that 90 degrees plus 90 degrees minus X, and that gives us 180 minus 180 plus X, which is equals to X. So D2 equals to X, meaning that therefore AB equals to is the tangent. Therefore AD equals to X equals to therefore AB is the tangent. Therefore AB is the tangent. And the reason is converse of Tan-Chord theorem. Converse of Tan-Chord theorem. Or we can simply say those angles are equal. Now the last question goes, prove that AD squared equals to 4DO squared minus 4AB squared plus 4MB squared. Prove that AD squared, here is AD, prove that AD squared equals to all of that mess. We know that this is a right angle triangle, so DA squared will be equals to DC squared minus AC squared. Let's write that down. Okay. DC squared, you know that DC squared equals to DA squared plus AC squared. Pythagoras. Plus AC squared. But notice that we're given this in terms of other interpretations. So they used DO, instead of DC, so they use DO. All right, so we're dealing with DO. We're also dealing with AB, and AB we're dealing with AB. Let's see where AB comes from. And then we're also dealing with MB. All right, AB and MB. Okay, so this is also a right angle triangle, and this is where it comes from. AM is part of that. So DC squared equals to that, meaning that AD squared, let's express this, AD squared will be equals to DC squared minus AC squared. Okay, but DC is 2 times DO, and DO is part of what we need to express it. So the DO is coming out now. So DC is 2 times DO, already here, so we substitute that for 2 times DO all squared. Therefore AD squared equals to minus AC. AC is 2 times AM. So let's substitute that. So that will be 2 AM all squared. Because this is the midpoint. So AM is equals to MC. The whole of AC can be expressed as 2 times AM. Now we have AM in this small right angled triangle. Let me highlight it for you in red, so in green, so you can see this right angled triangle. AM can be expressed as AM squared can be written as AB squared minus MB squared, and they are both there, they are represented. So let's express that as ABN, so that is 2DO all squared minus 2. Okay, let's go 4. Okay, that will be okay. Let's 4DO squared. Let's okay 4DO squared minus 4AM squared. Now let's substitute AM squared for AB squared minus MB squared. So that will be equals to, it is the hypotenuse, so that will be 4 in bracket. Instead of AM squared, we'll go AB squared minus MB squared. AB squared minus MB squared. There we go. Now we can expand. That gives us 4DO squared minus 4AB squared minus negative, that will be plus 4MB squared. Let's check if that is the original. Yes, minus 4AB squared. Excellent. Plus 4MB squared. Therefore AD squared. There we go. Done. We've proven that. And with that, we've come to the end of this paper. Yes, we've come to the end of this paper. Thank you so much for watching. I'll see you in the next